All right, everybody, good afternoon. Let's get started here. Today we're covering 4.3 derivatives in the shapes of graphs, and then next time curve sketching and optimization. So I think we're pretty much on schedule in terms of our calendar. We are supposed to be starting today derivatives in shapes of graphs, so good. We do have a test scheduled for April 28th. So that is still in place. I don't plan on moving that at all. So let's see how things go this next week. And that will give us some idea of what will be on the test. Any questions before I begin? No questions? All right. So derivatives and shapes of graphs. There's a lot of notes here. Let me go ahead and open these up. So before I actually start, let me just say something about this. What we've done so far in this chapter is we've said, okay, if you have a function, right, as long as it's on a closed interval and it's continuous, right, so it's on a closed interval, as long as it's continuous, we can find the absolute maximum and minimum values of that function on the closed interval. So we can find the highest point, we can find the lowest point. We can do that so far. What we're going to do now is we're going to say, all right, well, let's no longer restrict the function to a closed interval. Let's just let the function be on some domain, not necessarily closed interval though. And let's try and find not the absolute max and mins, but the locals, right? These, we call these local maximums and minimums. We want to be able to find those. And to do that is actually related to what we've done, but it's a totally different technique. So whenever you've got a closed interval, we want to do things one way. Whenever you have a non-closed interval, I'll just say not closed, then we have a different technique. So this section is to get us started on how we would find these local maximums and minimums. All right, that's the motivation. So derivatives in the shapes of graphs. First definition, a function. We've already talked about what it means for a function to be increasing. Increasing means that if you were to be walking along this function from left to right, that you'd be going up. So I hope everyone would agree that this function here in blue is increasing, right? It's always going up as you go from left to right. But I want you to take a look at the slope of the tangent line at every point on this graph. Do y'all see that no matter where I am on this graph, the slope of the tangent line is positive? There's a connection here. If my graph is increasing, then the derivative has to be positive within this region. If my graph ever starts to go down, well, if my graph is decreasing, then my slope of my tangent line is going to be negative, right? And if the function is flat, well, then my derivative, my slope of my tangent line will always be 0 as I move from left to right. So that's what this first thing, this first note tells us. Let me make this a little bigger. Excuse me. It says here, if your derivative of your function is positive, greater than 0, on some interval AB, so within some region, if your derivative is positive there, then your conclusion is that the function has to be increasing on that interval. On the other hand, if our derivative is negative on some interval, then our function must be decreasing there. And if the derivative is 0 on some interval, then our function must be constant, must be flat. Does that seem reasonable to you to make that connection now between the slope of the tangent line and the increasing and decreasing of a graph? It's not a big stretch, right? And it seems to the geometry of it makes sense. So that's the first idea here. Okay, where do we go with that? Let's take a look at a function here, just again to illustrate this function. It goes up, then down, up, and then back up. So when I'm over here on this region, I am increasing. When I get to the top, my derivative is 0. Then I start decreasing, so negative derivative, and then flat derivative, and then I'm going to increase, my derivative is going to be positive again. So my derivative went from positive to negative, then back to positive. And notice that where we had those changes, right, where I switched from positive to negative right there, that's a local maximum. And when I went from negative to positive right here, that's a local minimum. So maybe we can use this somehow to help us figure out where these local maximums and minimums are. So this leads us to the first derivative test. All right, this is a test that we can use. Suppose that C is a critical number of a function. All right, so critical numbers we studied in 4.1. A critical number is anywhere that the derivative is 0 or anywhere that the derivative doesn't exist. So this test says, hey, let's say you found a critical number, all right? You found this critical number. And then you determine that the derivative changes from positive to negative at that number, from positive to negative. Then the conclusion is that you must have a local maximum there. So look at this picture. Everyone see that we have a local maximum right here at this point? Right at this top point? Let's see, yeah. Right here, we have a local max. Look what happens. At that point, right? At that point, get up there. Get up there. Oh, it's not going to let me. Hold on. Nope, I'm not going to be able to get it. Trying to get it to be 0. Okay, we're just going to have to live with it. At the top, though, at the top of this, I hope that you would all agree this is a point C where the derivative would be 0, right? So that means that this is a critical number. That's a critical number of our function because it's a place where the derivative is 0. And notice that to the left, right, our derivative is positive, and then to the right, our derivative is negative. And therefore, this test says that has to be a local maximum. If you change from positive to negative on the derivative, okay, on the derivative, then you have a local maximum at that point. On the other hand, if you have a critical number and your derivative changes from negative to positive at that point, then you're looking at a local minimum. So that would be this point over here on this side. Let me go there. So over here, you can see that at the bottom, again, we have a flat tangent line. So at C, right, at C, that's a critical number. And the derivative changes from negative to positive, right? So anytime you change from negative to positive, as you move from left to right, you should be looking at a local minimum. And then the last part says, if you've got a critical number and the derivative does not change signs at that point, it doesn't change. So it's either like goes from negative to negative or positive to positive, then F has no local max or min at that point. In other words, it doesn't qualify. So that an example of that would be right here in the middle here. Notice that at this point right here, it looks like we have a flat tangent line. So at this value C, we have a critical number, but on the left side, our derivative is negative. And as soon as we go past C, our derivative stays negative, right? There's no change in sign on the derivative. It goes from negative to negative. So therefore, that's not going to be a local max or local min. If it went from positive to positive, same story. It would not be a local max or min. All right. So there's our maximum. There's our minimum, right? And this is where we don't have either one happen. All right, let's work with that. Okay, let's just start with that and then we'll move on. There's another section to this, to the notes. So I'm going to give you a function. We'll start off simple. Let's say we take the function f of x equals x cubed minus 9x squared. And I would like for you to find where this function f is increasing. Now, I'm not going to write that from here on out. From here on out, instead of me saying f increasing, I'm going to do this. Find where f, and I'm going to put a little arrow going like that. That's going to mean f is increasing. All right, so that's part A. Part B, I'd like you to find where f is decreasing. So I'm just going to put an arrow down like that. And then part C, I want us to find any local maximums or minimums. All right. Okay, let's go with this. So now we have to put everything that I've just said together into like a method. All right, so here's what I'm going to do. First thing I'm going to do is I'm going to find the critical numbers, because the critical numbers are going to be the numbers that help me figure out what's going on, right? So we need the derivative. Okay, derivative should be straightforward. F prime of x is 3x squared minus 18x, right? That's our derivative. And now to get the critical numbers, I have to do two things. First thing I need to do is figure out where the derivative is 0. And the second thing I'm going to need to do is figure out where the derivative doesn't exist. So where the derivative is 0, all I'm going to do is set the derivative equal to 0. I can factor out GCF 3x. I'll be left with x minus 6 equals 0, and then set those both to 0. I get two solutions, 0 and 6. Now, notice we're not talking about a closed interval anymore, right? When I gave you this function, I did not ask you to find anything on a closed interval. I just gave you the function, right? So we do want to make sure that these points are in the domain of the original function, but we don't need to worry about whether or not they live inside some interval like we did in 4.1. The domain of this function is all real numbers because it's a polynomial. So we have no issues with these critical numbers. These are both, right? These are both critical numbers. Now, figuring out where the derivative doesn't exist, all I need to do is take a look at the derivative and make sure that there's no issues. And when I look at that derivative, again, that's a polynomial, 3x squared minus 18x. I never have to worry about division by 0 or square roots of negative numbers. We don't have any sort of issues with plugging values into that. So that means I don't get any sort of critical numbers from that. Are we good? Okay, so we have the critical numbers. Here's where things change from what we did in 4.1. What I'm going to now do is try and figure out if the derivative changes signs as I move from left to right. Is my derivative going from like positive to negative or negative to positive as we move from left to right through these critical numbers? So the most efficient way to do that is this. We're going to draw a number line. And I'm going to plot my critical numbers on a number line. Here's 0, here's 6. And then I'm going to put dotted lines going straight up. These are not vertical asymptotes or anything. What all the dotted lines do is help me realize that these two numbers break up our number line into 3 regions. I have the region to the left of 0, the region between 0 and 6, and the region to the right of 6. And what I'd like to know is what the derivative is doing in each of these regions. So it's kind of like I'm asking, okay, what is the derivative doing over here? Don't write this down. What's the derivative doing here? What's the derivative doing here, right? The derivative will tell you whether or not your function's going up or down, right? So the way to actually do that is to pick some test points. So I'm going to pick some arbitrary values. Anything I want to the left of 0, I'm going to pick -1 because that's a nice point, right? I'm going to pick a point between 0 and 6. Let's go with 3. And then some point to the right of 6, which I'm going to pick 9. I don't know why I picked 9. I could pick 7, 8, 9, 10. I could have picked 1,000,000. It doesn't matter. It just has to be to the right of 6. And what I want to know is whether or not the derivative is positive or negative in this region. So I'm going to take those test points and I'm going to plug them into the derivative. So I'm now going to test f prime. Okay, I'm going to test f prime to see what it's doing. So that means I want to know what's happening. What's f prime of -1? What's f prime of 3? And what's f prime of 9? Please do not confuse this with what we did in 4.1. In 4.1, when we were on a closed interval, we found the critical numbers and we plugged the critical numbers and the endpoints into the original function. Remember, right? It was always the critical numbers and the endpoints into the original function. When you're dealing with a function like this, where it's not on a closed interval, you're finding your critical numbers, but you're not plugging those into anything. What you're doing is you're using those critical numbers to create regions, and then you're getting test points, and those test points are going to go into the derivative, not to the original function. So let's do this. Derivative, my derivative is right here in yellow. So I'm going to plug -1 into that. So when I do that, I get 3 times -1 squared minus 18 times -1. And this will be equal to, let's see, 3 plus 18, which is 21. But all I care about is that this is bigger than 0. Because that tells me that the derivative, right, at that point, the derivative at -1, right, is positive, right? It's positive. Right, my derivative is positive, or you could say it this way: the derivative is greater than 0. Same thing, right? A derivative is greater than 0, which means that over here to the left of 0, what should my original function be doing over here then? If my derivative is positive, what's my original function doing over here?
It's increasing.
Increasing, right? So this tells me that the original function, not f prime, the original function is increasing over here. Okay, let's do the next one. What if we plug in 3? Plug in 3, we get 3 times 3 squared minus 18 times 3. This is going to be 9 times 3 is 27. And then minus, what is that, 30, 40, 54. So we get -27, I believe. But that's less than 0, right? That's a negative number. And because it's less than 0, that means my derivative at that point is negative, which tells me my original function in that region is going down, right? Negative derivative means we're decreasing. Positive derivative means we're increasing. And then finally, let's plug in 9. And I don't know, I'm not even going to do it, but this will come out to be positive, okay? So whatever this is going to be a positive number, all right? I'm not going to show the work for that. And then this means that the derivative at that 0.9 is positive, which tells me again that my original function is going up here, right? So I'm going to come back up to my, the little number line that I have here. I'm going to put something up here and just so you can kind of see it, all right? What I know is that over here to the left of 0, my original function here is going up. Then between 0 and 6, my original function is going down. And then my original function is going up. So I go up and then down and then back up, right? That's what it does, up and down and up. And I also know that 0 and 6 were critical numbers, right? Those were critical numbers. So that means since it goes up and down, you can almost kind of think of like what the graph would look like. It has to go up and then back down, right? And then over here, it's got to go down and back up. So we should have a local maximum here at 0, and we should have a local minimum here at 6. Understand? So let's answer the questions now, all right? First question was, find where f is increasing. Let's answer that. So where is my function increasing? Look at it. Everything to the left of 0, my function's increasing. Everything to the right of 6, my function is increasing. So I'm going to answer this by giving the x values where my function is going up, which means everything to the left of 0, everything to the right of 6. I will write it this way. Negative infinity to 0, union 6 to infinity. So just keep in mind, these are the x values, right? The x values where f is going up, increasing, right? It's kind of like asking for you asking you to give me the domain of something. You look at the x values. When we're asking where a function is going up or down, you're looking at the x values where it's going up and down. Questions on that? Students will ask me sometimes, could we include 0 and could we include 6 in this answer? Like, could I put a bracket on the 0 and a bracket on the 6? The answer is yes, you can include a bracket, but having a parenthesis does not make it wrong. So sometimes you can't have a bracket. When we get to an example, I'll show it to you. So my rule of thumb is whenever you're doing increasing, decreasing, just always use the parenthesis. Just don't ever use a bracket. All right, where is it going down? Okay, so my function is decreasing. Well, that's happening here in this green region. So that's between 0 and 6. So I'm just going to go 0, 6. And again, those are just x values. And finally, find the local maxes and mins. All right, so let's talk about this. I have a local max. I'm going to put L max. Okay, my local max, where is it happening? At what x value do I have an maximum? At what x value?
0.
0, right? So the way to find the actual maximum value is to plug 0 into what? If I want to know how high the function goes at 0, I'd have to plug 0 into the original function, wouldn't I? So my local max is at the original function's value at 0. Can you tell me the original function's value at 0? Plug 0 in here. You just get 0, don't you? And then I have a local minimum, and that happens at 6 because we go down and back up. So this happens at f of 6, which means we'd have to plug 6 into this. So I'll just do that on my calculator real quick. I'm going to do 6 cubed minus 9 times 6 squared, negative 108. There we go. That's it. We've done it. We've answered the questions. Do you have any questions?
Can we do another one like this one?
Y is x cubed minus 9x squared. Okay, there's the graph of this function, okay? That's the graph on Desmos. Now I'm going to adjust this so we can see it. There's, if I squeeze the y-axis down, that's what we have, right? And do y'all see that at the point 0, 0, right? That's the point 0, 0. That's the same as us saying when you plug 0 into the function, you get 0, right? At that point, we have a local maximum. And then when we go to 6, right, that's this point here. This is 6 and then negative 108. And that's a local minimum. Notice that we're going up over here, increasing until we get to 0. Then it's going to decrease until we get to 6, and then it will begin to increase again. We could figure all of that out by figuring out the critical numbers and then running a test on the first derivative to see if it's going, where it's going up and down, and then putting it all together. Okay. All right, let's do another one. Just pick one here. Okay, that looks fun. How about this one? F of x is equal to 5x to the 2/3 minus 2x to the 5/3. And I want us to do the same thing that we just did. So same instructions here. I'm just going to copy them. So I want to know where f is increasing. I want to know where f is decreasing. And I want to know any local maximums or minimums. All right, well, we need a derivative, right? So we start with that. So go ahead and get your derivative. All right, this is not a polynomial, but it is still, we can use the power rule for these derivatives. So when I bring the power out and hit the 5 with it, it becomes 10/3 x to what power? You have to subtract 1, right? So
negative 1/2.
negative 1/3, right? Because you're going to take away 3/3 from 2/3. Next one comes out, you get negative 10/3 x, and now subtract 1 from 5/3. So take 5/3, subtract 3/3, you should get 2/3. Is that all right? That's our derivative, right? And that's it. We've got to now take this and find the critical numbers. So I need to know, first of all, where's this derivative equal to 0? And then what I need to know is where the derivative doesn't exist. Okay. Before we get into this too much more, I want us to look back at the original function. Are there any domain issues with that? What does the 3 on the bottom really mean here? When you raise x to the 5/3, the 3 really means what?
It's a cube root.
The cube root. It's a cube root. So like if you wanted to, you could rewrite this as 5 x to the 2nd power, but then cube root. And then you could have written this 2, and then you could have gone x to the 5th power and then cube root. The reason why I'm saying that is because there are not any domain issues here, because we're doing cube roots, not square roots. If it was a square root, then we can't plug in a negative. But if it's cube root, you can do cube roots of negative numbers. So we have no domain issues. This thing should be defined everywhere. The domain is negative infinity to infinity. I just want to point that out right now. All right, just want to point that out. We can plug any number we want into the original function. Now, this derivative, I have to set it equal to 0 first. All right, this is going to be a little tricky. All right. So the first thing I'm going to notice is that these both have a 10/3 in them, don't they? So, I mean, I could factor that out. Let me do that. I'm just going to pull a 10/3 out. And the reason I did that is because now I can just divide both sides by 10/3. And it goes away over here, and on the right side, 0 divided by 10/3 is still 0. Which means that the 10/3 is gone, and all I really have to do is solve this. Now there's a lot of different things you can do here algebraically, but let me just show you how I would do this, all right? I would notice that this one here, this first term, has a negative power. So I'm going to rewrite this as 1 over x to the 1/3 minus x to the 2/3 over 1 equals 0. Why do you think I put the second one and wrote? Why do you think I wrote it as a fraction? What do you think I'm about to do now?
Common denominators.
Common
No.
denominator. I'm going to try and put them together. Okay, I'm going to try and put these together. So that means I'm going to need to multiply this fraction over here by x to the 1/3 over x to the 1/3. That way they both have the same denominator, right? Okay, so I'll have 1 over x to the 1/3 minus, now when you multiply these two together, x to the 1/3 times x to the 2/3, what do you do with those powers, 1/3 and 2/3?
Just get added.
Add them. So what's 1/3 plus 2/3?
1.
1, right? That's 3/3, so that's 1. So that's just an x there, right? X over, on the bottom we have x to the 1/3, the common denominator now. And then we can put these together because they have the same denominator, so it just becomes 1 minus x over x to the 1/3 equals 0. Now, the reason I did that, now that we've done it, the reason I want to explain why I did all that. I did that because I know that when it comes to setting something equal to 0, if it's a fraction equals 0, all I have to do is look at the top, right? We've been through that a few times now. So all I really have to look at here is when is 1 minus x equal to 0? And that's pretty easy. You just solve for x, you just get x is 1. So we have a critical number. X is 1. We okay? All right. The next thing I need to do, don't forget about this, I need to figure out where the derivative doesn't exist. So here's my derivative, right? Here's my derivative. And I did a lot of algebra here, didn't I? On the left-hand side, remember all this algebra I did? I could do that similar algebra, but because I don't have an equal 0 here, what I'm going to do is I'm going to bring that 10/3 out like we did before, right? And then I'd still have this x to the negative 1/3 minus x to the 2/3. And then this part in the parentheses is basically this, which we know turns into this, right? So we know that this is 10/3 in parentheses 1 minus x over x to the 1/3. Okay, I'm looking at that. That's my derivative. Are there any problems with this derivative? Are there any numbers you cannot plug into this?
0.
0, right? 0 cannot go in. If you plug in 0, 0 to the 1/3 is 0, right? And you'll get division by 0 here, won't you? Can I plug 1 into the derivative? I would get 0, wouldn't I? But it's not division by 0, right? So it's okay to plug in 1. I just can't plug in 0 because then I'll have that division. So I actually do have a critical number from this analysis of the derivative. I know from this that x can't be 0, so that means that x equals 0 is a critical number as well. So I have two critical numbers, 0 and 1. What do I do with those now? What did we do before? We found our critical numbers, right? 0 and 6. We put them on a number line. That broke our number line into regions. We pick test points. Those test points go into the derivative. That tells us where we're going up and down. And then anywhere we go up then down or down then up, that's gonna reveal the local max and mins to us. So I'm gonna put these on a number line. Make sure they're in the correct order, 0 and 1. I have to pick 3 test points. -1 will be a good one. 2 would be a good one. And unfortunately, I've got to pick something between 0 and 1. So I've got to pick a fraction or a decimal. I'll pick 1/2. Where am I going to take these numbers and plug them into? What am I plugging them into?
The derivative.
The derivative, right? Not the original function, the derivative, because that's going to tell us where we're going up or down. So I need the derivative evaluated at -1. I need the derivative evaluated at 1/2. And I need the derivative evaluated at 2. Now, when I say plug these into the derivative, you've got to go back to the derivative, which we have a couple of versions of them. I have this version of the derivative, right? That was the original version. But I also cleaned it up and made that version as well. I kind of like the second version over here because it would be easy for me to plug a number into this without having a negative exponent like here. So I'm going to choose to use this as my derivative. Just going to put it down here so we can see it. All right, so let's plug in -1 first. So we get 10/3. 1 minus, careful, -1, that's going to be +1. And then on the bottom, I'm just going to write that as the cube root of 1. All I care about is whether or not that's positive or negative. What is it? This is 1 plus 1, right? So that's 2 over the cube root of 1 times 10/3. Those are all positive numbers, aren't they? So this should be greater than 0. So if the derivative is greater than 0, what does that tell me about my original function? Going up, right? Going up. Now we got to plug in a half. Okay, the half might be a little harder. 10/3. Okay, 1 minus a half over the cube root of a half. So what about this? 1 minus a half, positive or negative? Positive, right? Okay, and then what about the cube root of a half? I don't know what it is, but is it positive or negative?
Positive.
Positive, right? Because the cube root of a positive number should be positive. And then you're multiplying by 10/3, which is positive. So they're all positive as well, right? Everything's positive. So this should also be greater than 0, which means, again, that my original function is still increasing here, still increasing. And then we plug in 2. 1 minus 2 over the cube root of 2. And notice here that 1 minus 2, that's a negative number. And then everything in yellow is a positive number. So you have a negative divided by a positive, that's going to be negative, and then multiply times a positive again, you should be negative. So this will be negative, less than 0, which means that my original function now goes down. So back here, I go to the left of 0, I'm going up. Between 0 and 1, I'm still going up. And then to the right of 1, I'm going down. Let's answer the questions. First question, where's the function going up? Well, everywhere to the left of 1, right? It's always going up to the left of 1. I mean, it's going to the left of zero, it's going up, to the right of zero, it's going up. You could break this into two intervals. You could go like negative infinity to zero and then 0 to 1, or you just do the whole thing. I'm going to do the whole thing. I'm just going to say, all right, well, from negative infinity all the way to 1. Was it 1? Yeah, to 1. Okay, so from negative infinity to 1. Where is it going down? From 1 to the right. So I put 1 to infinity. How about local max and local min? All right, so let's see. Does our derivative ever change signs? Does the function ever go up and down, or then down and up, or something like that? Well, here at 1, right? At 1, we go up and down, right? So it's gonna look like that. That should be a local max. So we should have a local maximum at 1. When we plug 1 into the original function, plug 1 into this. 1 to any power is 1. So that's just going to turn into a 1, and that's going to turn into a 1. So you should just get 3 here. And then what about a local minimum? Do we ever go down then back up? Down and back up. As you move from left to right, do we ever go down then back up? No, right? So that means you have no, or just let's just put none, okay? We're done. I'm going to go graph it. I'll leave that up there for a second while I type this in. 5 raised to the, oops, 5x raised to the 2/3 minus 2x raised to the 5/3. Weird graph. What the heck? Something's wrong. Hold on. Decrease. Did I mess up my sign? Hold on.
I think it was at -1. In the first one, because the cube root
Oh
of
shit! I
-1
screwed
should
this
be
up.
negative.
Yeah, you should have spoken up. Look, everyone, I messed up. That's good. I like messing up every once in a while. Look, this -1 right here. This should have been a -1 right there. I think I just forgot to put, I think I put -1 here and told you to be careful with the negative, and then forgot to put -1 here. How does that change things? The cube root of -1 is what?
-1.
-1, right? The cube root of -1 is -1, right? Because -1 times -1 times -1 gives you -1. So that changes everything because this is now positive. The bottom is negative. That ratio is negative, and then you multiply by 10/3, you're still negative. That switches this to less than 0, which switches this to going down. Glad we looked at the graph because I would have just moved on. Everyone seeing this? That changes this to down. That changes all our answers, doesn't it? Changes everything. I'm sorry, everyone. Got a little mistake, huh? Makes a big difference. We're going down, then up, then down. So we have a local max here at 1, but we have a local min at 0. And we also have to change the intervals where it goes up and down. So let me tweak my answers. Just go back up here and change these. Okay, I'll leave that. That's still the same. The local max is the same. The none is not there. Okay, so where is the function going up? Only between 0 and 1. Where is it going down? To the left of 0 and to the right of 1. So the way I'll write that is -infinity to 0, union 1 to infinity. We already found the local max because that's where we went up and down, but now we also have this thing where we go down and up. So we have a local minimum at 0. So I will plug 0 into the function. And when I plug 0 into the original function, I should get 0. Okay. Now the graph will make sense. So here's what this graph looks like. Hey, what is this thing at 0? What is that shape where it comes together like that? What do we call that?
Cusp.
Cusp, right? Doesn't the derivative not exist at a cusp?
Yeah.
Okay, and didn't we find that out right here when we did this part? Where's the derivative not exist? We said, oh, at 0, it doesn't exist, right? That matches with the cusp. So our function goes down, then up, and then back down. We have a local max there. At 1, you get 3, and we have a local min right there. At 0, you get 0. Interesting function, huh? Interesting looking function. Okay. Let's do another one. X squared minus 4 over x squared plus 4. Same questions as before. Still on my. Ah. Okay. Take your derivative. I'll give you a minute, take a derivative, do it on your own. And then try and see if you can set the derivative equal to 0. All right, take a few minutes, see how much of that you can get on your own. Are y'all ready for me to reveal the work for it? Ready to see it? Give you a minute to look at it. Do you have any questions on the derivative quotient rule? Everyone okay with that? Distributing the 2x, negative 2x through, you get some things to cancel. You can combine like terms, get 16x over x squared plus 4, that quantity squared. And then I go do the two things, right? I have to set it equal to 0, the derivative, and then figure out where it doesn't exist. Where I set it equal to 0, well, it's already a fraction, right? So I just set the top to 0, 16x equals 0, divide by 16, you get x is 0. And then why did I say, why do I not care about where it doesn't exist? Why did I just cross it out?
It's never gonna be 0 at the bottom.
Yeah, there's no x you can plug in to get 0. Because you're gonna be, whatever you plug in here, you're gonna square it, right? So at the bare minimum, it's gonna be a positive number. It could, well, bare minimum would be 0. If you plug 0 in there, you get 0 squared is 0, but you still add 4, right? And then you square it. So there's no way that that's ever going to be 0 down there. Now, had it said x squared minus 4 on the bottom, well, then you would have two solutions, 2 and negative 2. So we're okay? We only have one critical number, which means when I draw my number line, it only splits the number line to 2 regions. So I've got to pick a test point here. How about -1? Pick a test point here, like a +1, and plug those into the derivative. And all I care about is whether or not I get a positive or negative. So I'm going to be really careful here because I screwed up the last one. Here's my derivative here in yellow. What can y'all tell me about the denominator of this derivative? What is it always going to be?
It'll always be positive.
Positive.
Always positive, right? Okay, so all that really matters is what's happening up on top. So if I plug -1 in, 16 times -1 is -16. So this is going to be a negative number. This will be less than 0. That tells me that the original function is going down there. And then if I plug in 1, I get 16 times 1, that's 16 on top, that's positive. And that's going to tell me that my original function is going up over here. So for here, our original function goes down. Here, our original function goes up. Is 0, I didn't say this, but 0 is in the domain of this function, right? 0? Can you plug 0 into this? Yeah, you don't get division by 0, right? So, and this function actually has no domain restrictions because, yes, I agree, 2 and -2 will give you 0 on top, but that's okay. You can never make this denominator 0. So the domain of this is all real numbers. So our critical number is valid. And so we can conclude what we need to conclude here. Our function is always going up to the left of 0 and going down, I'm sorry, to the right of 0, and then always going down to the left of 0. And in terms of local max and mins, local max, what do you think? Do we have a local max?
No.
No, it
No.
never goes up and back down. So we don't have any here, none. And local minimum, well, we do, right? At 0. So when we plug 0 into the original function, let's see what we get when we plug 0 into the original function. You get -4 on top and you get +4 on the bottom. So that's -1. We're done. Get that graph going here for you. It's the graph of the function. Notice that at 0, right? At 0 down here, we have that point 0, -1, right? That's a local minimum. Notice that to the left of 0, our function is decreasing. But as soon as we get past 0, it starts to increase, right? We've determined all that, haven't we? So this section is called, derivatives and the shapes of graphs, right? Right now, what we're doing is we're using the derivative to tell us where a function is going down, where it's going up, any highest and lowest points that we have as we're moving across from left to right. That's something you couldn't do in college algebra. Even when you were studying polynomials, you could tell whether or not your graph's going up and down and how many wiggles it has, and you could find x-intercepts. But you can never figure out like the peaks and valleys, generally speaking. Now we can. We can actually find peaks and valleys for polynomials. All right, any questions? We got to move on to the second idea of this section, which is very much related to this. So this is not going to be like completely out of left field here. All right, so the first derivative, right? The first derivative of the function tells us about where the function's going up and down. The first derivative is positive, the function goes up. If the first derivative is negative, the function goes down. But what about the second derivative? It turns out that the second derivative of a function tells us something else about the way the graph looks. And it has to do with what's called concavity. All right, so that's what we're going to study now. Concavity. And then this thing called inflection points. All right, so I want you to look at this function right now. Just look at it first, all right? What we've studied so far has to do with where the graph goes up and down, right? Up, where it goes up, where it goes down, where it goes up, where it goes down. So I want you to see, I'm gonna move this thing around here, and I have the computer right now. I have the computer calculating the second derivative for me. So the second derivative, remember, is not the slope of the tangent line, right? That's the first derivative. So the computer's calculating the second derivative for me. Every time it calculates and gets a negative, it's going to leave a red trail behind it. And if it's positive, it's going to leave a green trail. So there we go. Everywhere you see red, the second derivative is negative. Everywhere you see green, the second derivative is positive. You're just going to have to take that on faith. So notice this red region on the left side. Notice that this shape of this graph over here, right? The shape of the graph over here looks like the frown, like a smiley face. It looks like the frown on a frowny face, right? The graph right there looks like a frown. But in this little region right here, from here to here, you actually look like you're part of a smile now, right? This green part is like part of a smile. And then right here it switches and now it's part of a frown again. And then it switches back to a smile. See that? Frown, smile, frown, smile. That's what the second derivative tells you. Your second derivative tells you whether or not you're smiling or frowning. Now, we don't call it smiling and frowning, we call it concavity. So if you're frowning, it's called concave down. If you're smiling, it's called concave up. All right, that's the idea, that's the definition. I'm going to show you the notes again here. But do you see visually what it is? Frown and smile. You'll see the frowns and smiles there. Okay, so to this. If the second derivative of a function is positive on an interval, then it is concave up on that interval. So second derivative positive means you look like a smile. Second derivative negative means you look like a frown. And that's easy to remember because positive people normally smile and negative people are usually frowning, right? So when your second derivative is positive, you're happy, and your second derivative is negative, you're sad. That's the way the graph looks, okay? Now, any point where you have a change in concavity, meaning you go from a smile to a frown or a frown to a smile. It doesn't matter which way. It's either, it can be the smile to a frown or frown to smile. Anytime that happens, the point where it switches is called an inflection point. So when you look at this graph right here, this graph would have several inflection points. That would be an inflection point. I'm just going to put IP for inflection point. This would be an inflection point, IP. And this would be an inflection point, IP. And the reason those are called inflection points is because that's where you have a change in concavity. Anytime there's a change in concavity, you have inflection points. Okay? So now what we can do is we can go and do problems where I ask you for everything I've asked you so far, right? I can give you a function, I can say, hey, tell me where it's going up. Tell me where it's going down. Tell me local maximums. Tell me local minimums. And now I can say, all right, now tell me where it's smiling. Tell me where it's frowning. Tell me where you have inflections. So how do we go through it, right? How do we go through the procedure? What is the process? Well, it's very much the same as this process, right? In this process, to figure out where the function was going up or down, we looked at the first derivative and we played this game with the first derivative, right? We found like the critical numbers, we did a number line, we tested the points. We're going to do the exact same thing, but to the second derivative. So we're going to take the second derivative, we're going to figure out where it's zero, where it doesn't exist. We're going to create a number line, we're going to pick test points, we're going to plug those into the second derivative, and that will tell us concave up or down. Does that kind of like just theoretically make sense what we're about to do? Theoretically? No. Let's do this problem. Okay, let's do the very first one we did. This one right here. Okay, take this problem. All right, and we have already answered a bunch of stuff, right? Let me actually go to where we answered it, which let me just grab all of this. Okay. Okay, so check, we've done all this, right? We've got all this covered already. It's everything we just learned. But now I'm going to add a couple more things. Part D. Find where f, the original function, is smiling, right? Concave up. To say that, I'm going to draw a little like U like that. That kind of lets you know it looks like a smile. So what this really means is I'm asking you where it's concave up, all right? And then part E, I want you to find where the original function f is concave down. And then part F, find any inflection points. All right. Do y'all see how these three questions are pretty much the same as these three questions, but we're going to be operating on the second derivative instead of the first? So let's get the derivative. We already know the first derivative. We did that earlier, right? The first derivative of this function was 3x squared minus 18x. And we used that to get all of this parts A through C, right? Parts A, B, and C we did looking at the first derivative. Now let's look at the second derivative. So we'll do that here. My second derivative of this function is 6x minus 18. Nice, clean second derivative, huh? Let's now take that second derivative and find critical numbers. Let's figure out where it's 0. Let's figure out where it doesn't exist. So first thing, where's my second derivative 0? Second thing I'm going to do, where does the second derivative not exist? All right, setting that equal to 0, you should be saying thank you. That's easy, right? X is 3. And the second derivative not existing isn't even an issue because the second derivative is a line, right? 6x minus 18, it's a linear, so it's always defined. No issues. So I only have one number to put on the number line. 3. I pick a point to the left, I pick a point to the right. So I'll pick 2 and I'll pick 4. And where are these points being plugged into, these test points?
Second derivative.
To the second derivative, right? They're going into the second derivative because the second derivative being positive or negative is what tells me about concavity. So I want the second derivative at 2. I want the second derivative at 4. Okay, second derivative is right here in blue, right? So just plug 2 in there, you get 12 minus 18, right? 12 minus 18 is -6, but that's a negative number, right? That's all that I care about. It's my second derivative is sad, right? Which means my original function should be concave down over here. Second derivative negative means original function concave down. Now, when we plug in 4, you get 24 minus 18. That's what, +6? That's bigger than 0, right? And that means it's positive. Positive people smile. Original function is smiling over here, concave up. So on my little chart here, original function concave down, original function concave up. Questions, comments, concerns, complaints, gripes? Does someone want to yell at anything? No? Y'all all right? All right, so where's the function concave up? To the right of 3, right? To the right of 3. So I would say that like this. I would say from 3 to infinity. Where is the function concave down? Oh, to the left of 3. -infinity to 3. Inflection points, do I have any? Do you ever have a change in concavity? Do you ever go from smile to frown or frown to smile? Yes, at 3, right? At 3, you have an inflection point. So I could go f of 3 to figure out, it happens at 3, right? That's where it's happening. But to actually find the point, I'm going to plug 3 into the original function to figure out the y value, just to have it. So if I plug 3 in here to the original, I get 27 minus 81, is that right? So what is that? I can't do this arithmetic. 60, 50, 56? What is it, 50? What is that, 50? I can't do it. My brain stopped doing arithmetic a long time ago. It said, no, I need that space for other things. What is that, negative?
54, should be 54.
54, -54. That's just, I mean, that's just to have, okay? I don't really, the main thing about the inflection point is knowing where it happens. It happens at 3, but I always say just plug the 3 into the original function, and that way you have like a point. Let's go look at this function, okay? Let's go look at this function. No. I got rid of it. It was x cubed minus 9x squared. Was that it?
Yeah,
Okay, that was it. All right. So we had looked at this earlier. And let me kind of make it look better. Here we go. All right. So we had already, right? We had already figured out the local max and min, right? We got that from part C. We also knew where the function was going up and then down and then up, right? We knew that already. But now what we've done is we found this new thing. We found an inflection point, and it happened at 3 right there, right? Here's my x value of 3, and the y value there was -54. So 3, -54. There's something important happening here. To the left, I look like a frown the whole time, right? And to the right, it looks like a smile, which it does, right? That's exactly what it looks like. So the way I want you to think about this is before graphing calculators were readily available, right? I mean, there was a point where having a graphing calculator next to you was unheard of. Like there was calculators, but there weren't graphing calculators. So back in the day, which wasn't that long ago, we're talking about within the last, what, 70 years? That's a long time ago, but right, calculators and computers, like, I don't know, what would you say, like the 70s or 80s? The 80s graphing calculators probably became pretty, like, not common, but you could get them. So the last 40, 50 years, we had the ability to graph things. Now, shit, we've got Desmos. We've got things like this. We just go to a website. You don't even have to own software. You just go to a website, you can graph. Before that, though, how do you graph functions accurately? This is it. This is it, exactly what we're doing right now. We could take a function. We wouldn't know what it looks like because we don't have a computer to go to. We don't have anything to go to. So to figure out what it looks like, we start analyzing the first derivative and the second derivative. And we start putting all the ideas together to draw a picture. It's kind of obsolete at this point, right? Because it's so easy to graph things that you don't need it. But it's still an important skill because what you have to do is understand what's going on, right? You have to understand that the second derivative has to do with concavity. The first derivative has to do with increasing and decreasing of the function. Those are still important aspects of things. I'll give you an example. I don't know if I told you all this story. If I did, I apologize. I'm going to tell you again. I tell you about the Valentine's Day. My old office mate, Valentine's Day was, no? Okay. So when I was in graduate school, I waited tables, right? And we used to, I don't know if any of you have waited tables, but usually in the back, in the kitchen, there's a board. And if there's any items that are like 86th for the night, which means you're out of tomatoes or, you know, hey, we don't have this or that, they'll put it up on the board or they'll put notes on the board. So I would always put math problems on the board, right? I would go into work and I'd put a math problem up, and then there were some other people who were like in school, engineering and stuff like that. And we would each like throw problems up there. Well, I got into a habit of that. So when I started working at the college, my office mate, it was a bunch of us in a room, okay? And we would put problems up there for each other. And we just got to talking one day, and we were just bullshitting because it was like almost Valentine's Day. And he was like, yeah, I'm gonna tell my girlfriend that if she were to graph my love for her as a function, that the first derivative would always be positive. Okay, I guess his girlfriend at the time was somewhat mathematically inclined, so she would have understood this. So he's telling me that he's going to try and like woo his girlfriend with romantic math stuff by saying to her that his love for her has a positive first derivative, which would mean that it's what? It's always increasing, right? It's always increasing. Does that make sense? Oh, that's romantic. Well, then I challenged him and I said, what about this though? What if you have this? a function that behaves this way. And asymptotically approaches a horizontal line like this. Okay, so this is asymptotic. It is getting closer and closer to that dotted line, but never getting there, right? This function f would have a positive derivative always, you know, from 0 to infinity, it would always be positive. But, and yes, you could argue that his love is growing, but it is capped off, right? There's a limit to his love. Like, you know what I'm saying? So I told him, I said, you gotta be careful with that, man. You can't, that's not a strong enough thing you need. You need one more condition. What other condition could he throw on here that would be even more romantic? I'm kidding, it's not romantic, but you know what I mean. Look at the function. This is tied into what we're doing today. Yes, the first derivative is positive. Yes, the love is growing, but right now it's bounded. It could be bounded. It doesn't have to be, but it could be. But if he throws one more condition on this, he can make it unbounded, unbounded love. No. Think about the second derivative. What is the second derivative of this function? Positive or negative? Does that look like a frown or a smile?
It's negative.
It's negative, right? This is a function where the second derivative here, right, is negative. We don't want that. If I change that and I tell you it has to be positive, then could it be this picture? It can't be this picture, right? It would actually have to go like this now. And that could never be bounded above, because you would have to still increase, but you'd always have to look like a smile. So you would, there's no way you could be asymptotic. So I just said, hey man, that's awesome. Just make sure you tell her that the second derivative is also positive. And then you're good to go, right? Does that make sense? So like the whole point of me telling you that story is like, there's a difference between saying, hey, you know what, we don't really need to know this stuff because, you know, we have graphing calculators now. There's a difference between that and saying, you know what, it is important that we know this stuff because it's an understanding of what's happening with the function and how the derivatives impact the shape of that function. Let me give you another example. This is not a real world like me example, but this is a real world example. I'm going to show you an example of a graph where, let's say this is time, and let's measure it in like months. So this is like January of 2022, and this is February, right, of 2022, whatever. And then let's say this is a company and this is their profit, okay, the money they're bringing in, right? And so they're sitting there, you know, go to your meeting with your colleagues and you're looking at, you know, your company and you notice this, you've got profit like that. Okay. So look at that. I think overall, your company should be happy because your profit is increasing, right? Your profit is increasing. But something critical is happening here. There's a certain point on this graph where something happened, and it's right around here. It's where the smile became the frown. Do you see that point? Do you see the inflection point? The way you can think about this inflection point in this particular example is that when you're to the left of this, look at the slope of your tangent lines. They're positive, aren't they? They're positive. And to the right of this, they're also positive. But what's happening to the slopes of the tangent lines as I move to the right? What are they doing?
Plateauing, becoming straight.
Right? They're flattening out. So it's like, yes, you are still making money, but not as fast as you were, right? It's like, yes, look at our profit was growing, 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 and then, yeah, it's still growing, but it's starting to flatten out. In business, this point is called the point of diminishing return. It's an important point in business models because it's a point at which something happens. So you would go and you'd look, okay, February, oh, that was February 14th. What happened then, right? I don't know. I didn't want to, I wasn't trying to make it Valentine's Day or anything like that or close to it. Let's just say that was February 8th or whatever. You'd say, ah, that's when we hired that guy, Robert, right? That's when we brought Robert DiGiovanni on board. He must be doing something wrong because look at, he's affected our profits. He's diminished them, right? So, I mean, but that's something you would want to look at as business. What is happening at that point of diminishing return? But it's an inflection point. So that would be where the second derivative is 0, right? That would be a critical number of the second derivative. Okay, enough of me talking. Shall we do this one? We've already done part of it. How about we try and answer the same questions for these? I'm going to give you this function, all right, which we've already started working on. Feel free to use that whole thing about the function, you know, the love for your partner, you know, whatever. If you'd like, I'm okay with you stealing that. If you want to tell them the first and second derivatives are positive, you know, if it helps you out, go for it. All right, so we've already answered these first ones, right? Got that, got that, got that. Now I want these other things. So let me go back to the work. Let me grab, we took the derivative, didn't we? At some point we did. Where the hell is the derivative? There it is. Okay, we had taken the derivative, here it was, right? 16x over x squared plus 4 squared. That was our derivative, first derivative. So as a reminder, our first derivative over here on the side was 16x over x squared plus 4 quantity squared. All right, where's it concave up? Where's it concave down? You need the second derivative, right? And then you need to set it equal to 0. Go for it. I'll start working it, but I'm going to freeze my screen so you can't see my work. Try and get the second derivative of that and set it equal to 0. Be careful with that second derivative because you've got quotient, but you've also got chain. So be real careful. Enjoy. Please answer the poll. Let me know if you have it. And what I mean is, have you set the derivative equal to 0 and solved it? I'm only going to go maybe another 30 seconds because I realize setting this second derivative to 0 is going to maybe be a problem for some people. So okay, let's take a look at the second derivative. Make sure, first of all, you got the raw derivative correctly or correct. Take derivative of the top, 16 times the bottom, which is the whole bottom, even with the squared, minus, now when you take derivative of the bottom, you've got to do a chain rule because it's all of this squared. So first I bring the 2 out, that's this. Then the x squared plus 4 to the first power times the derivative of what's in here, which is 2x, and then finish off by multiplying by the top. All of that over the bottom squared, but when you square something squared, you get the 4th power. So I hope everyone at least got that part right. And we got to set that equal to 0. Come on, man. Okay, so I'm taking the second derivative, setting equal to 0, which means I'm going to take this and set it to 0. Which means I only have to look at the top, right? I only have to look at the top. Which, okay, we'll do that. We'll just look at the top. Set that to 0. Now I know that your instinct may be, let me just multiply all this out, which you could do, but there's something even better. And that is to look at this as being 2 different terms, like all of this minus all of that, and look at each of those pieces and try and find a GCF. So I see that they both have a 16, right? There's a 16 here and a 16 here. I can pull that out. And they both also have at least one of these factors, x squared minus 4 or x squared plus 4. This one has 2 of them. This one has 1 of them. So I can pull one of them out. So I'm going to do that. I'm going to pull an x squared plus 4 out. Now, what's still here? Well, I pulled the 16 out of the first one, and I pulled one of these factors out, which still leaves me with an x squared plus 4. Is everyone clear on that? Now, on the other one, I have the minus, right? Okay, the 2 here did not come out, so it's still there. This one I did pull out. The x squared plus 4 did come out because there was only one of them, and I pulled one of them out, so I have this is gone. I still have the 2x. The 16 is gone, but I still have an x equals 0. Let me just clean this up. 16 x squared plus 4 x squared plus 4 minus 4x squared equals 0. Oh, I guess I could put those together, huh? The x squareds in the second parentheses. I should have negative 3x squared plus 4 equals 0. And now all I have to do, because that's pretty much factored, I can set each factor equal to 0. So when I set that equal to 0, well, 16 can never equal 0, so that's gone. Don't worry about that. How about when I set this equal to 0? No solutions, right? Because if you move the 4 to the other side, you get x squared as negative 4, and there's no real numbers that'll work, so no solution here. Now this one, negative 3x squared plus 4, that equal to 0, that I can solve. And there's different ways to go about this. I'm going to move the negative 3x squared to the right to make it positive. I'm going to divide both sides by 3. And then I'm going to take the square root on both sides. So means I have to do plus or minus square root of 4/3 equals x. And then on my calculator, I'm just going to do the square root of 4/3 real quick. Just so we can get an idea of what these numbers are. It's plus or minus about 1.155. I'm rounding a little bit. X is approximately plus and minus that. I have 2 critical numbers there, right? There's 2 critical numbers. Any questions? This factoring out that I did here of the x squared plus 4, be on the lookout for things like that. Be on the lookout because that will drastically help you. All right. Number 2, I need to figure out where the second derivative doesn't exist. And where's my second derivative? Right here. Well, that's only going to have a problem if the denominator is 0. And we already talked about this. X squared plus 4 can't be 0. So no issues here. So I'm going to go now and put these 2 numbers on a number line. I have negative 1.155 and I have positive 1.155. And then I'm going to pick some test points. How about negative 2? Ooh, 0 is a good one between these 2. And then 2. And these are getting plugged into the second derivative. And we're going to try and figure out if we are smiling or frowning basically from that. So my second derivative at negative 2, my second derivative at 0, my second derivative at 2. And gosh, that's going to suck. Isn't that going to kind of suck to have to plug these in? Because I've got to plug it, I got to plug it into this, right? Got to plug in this. So watch what I do here. This is actually going to be pretty clever. Watch. This is going to be, you're going to like this. Here's my second derivative. I got to plug those numbers in there, but I'm going to use the fact, didn't we take the numerator over here and didn't we like do all this work and factor it down to this? So I'm going to take this and I'm going to put that in the numerator instead. Now, the reason I'm doing that is because this is much easier for me to plug numbers in and tell what's going to happen. See, 16 is always positive. X squared plus 4, that's always positive. And x squared plus 4 to the 4th power is always positive. So all of these together are positive, right? So all I really care about is what happens to this. That's all I really need to know. So let's try negative 2 in here. Negative 2 squared is 4 times negative 3 is negative 12 plus 4. That's a negative number. So this is a negative number, right? Which means that the original function is unhappy. When I plug 0 into this, I get positive 4. So everything's positive. So now I know that's positive, which means now my original function's happy. And then when I plug in 2, I would get the same thing that I get when I plug in negative 2. So I'll get a negative again, which means my original function is now sad again. So we go from concave down to concave up to concave down. Two inflection points, right? Two inflection points here and here, because we changed negative to positive, positive to negative, two inflection points. And I think you could figure out where it's up and down, just do the intervals. I wanted to go back and look at the graph though. I think I accidentally deleted it. Let's see how far back it'll let me go. There it was, right? That was it. So what was it? 1.15, something like that? Was it at 1.15? So let me see if I can find 1.15. 1.15, somewhere around here. It's right around here. And negative 1.15, somewhere around here. Those 2 points are where we go. What, to the left of that point, we've got frown here, right? Frown, that looks like a frown. Over here, that looks frowny. But then in here, we look smiley, right? All right, that's it. I want to just show you something. You may run across this in your homework. Let's say that you're doing a problem, okay? Let's say you're doing a problem and you get at the end that let's say that you get that the first derivative is this. 1 over x squared plus 1. Okay, just forget how we got here. Let's just say we get to that, right? And we're trying to find the critical numbers. All right, is this ever 0?
No.
No, because the numerator can never be 0. So there's no solutions here. Now, is the derivative never not exist? So is there anything you cannot plug in here?
No.
No, everything's good, right? So what happened? What does this mean? You have no critical numbers, right? You have no critical numbers. So that means if you go to draw a number line, there's nothing you put here, right? But you still don't know right now if your function's going up or down. You don't know. So what you're going to do is just pick any test point you want, anywhere. So I would pick 0, let's say. If I plug 0 in here, what do I get? Positive, right? So if I go f prime of 0, that's going to give me a positive number, which means my function is increasing. And that means that the function is always increasing. This just may happen. It may happen that you don't have a critical number. So what you still have to do is just pick a test point, and whatever happens, that's what's happening everywhere. Right? And then there was one more thing I wanted to say. Oh, so we have to make a decision in terms of like what to do. The next section we're supposed to do is basically called graphing, right? It's curve sketching, which is basically putting everything you've ever learned together, like college algebra, x-intercepts, y-intercepts, asymptotes, everything you've ever learned along here with the derivative, with increase, decrease, and concavity, put it all together to graph functions by hand. We could spend 4 weeks doing that. We could spend 4 months doing that, all right? I think what I've done in the past few semesters, because technology has become so easily available to people, is I've done like one simple problem out of that section where we go through and we show maybe 1 or 2 problems, that's it. And we keep it very basic and simple. And then we move on to the next section, because the next section is called optimization, and that's much more valuable information, because anybody can graph a function with a computer, but not everyone can optimize something, because that's where you have to interpret the word problem and turn the word problem into the math. So I'd rather spend 2 full days on optimization and cut back on the curve sketching. So I'm just letting you know that ahead of time, that I had the rationale behind it is that I feel like curve sketching is a little bit of an obsolete thing. So we aren't going to invest a whole bunch of energy into it. Okay. Have a good weekend. Try your homework for 4-3. I don't think there's any sort of things that you need to avoid there. you're gonna run into some interesting problems, definitely. Number 31, number 33, those are tough problems. 35, because it's got trig in it, so you'll be looking at my homework solution videos probably for some guidance on those. You've got the basic skeleton of what you need to do though, right? Have a good weekend, everyone. We'll see
Thank
next week.
you. Bye.
All right, take care.
I have a question.
Yes,
So it was the question 36 and 4.1.
okay, yes, I saw that. Do you mind if I keep recording and do it?
Yes,
Okay.
yes.
So it was 30, 35 or 34?
36.
36, okay, yeah, neither one. Okay, so it was f of x is x to the -2 natural log x. And you want to find the critical numbers, okay? So how did you do the derivative? Did you do a product rule or did you do something else?
First, I did the power one where I have to put in the -2 down.
Okay, so you brought it down as an x squared on the bottom?
Yes,
Okay, so did you rewrite the function like this and then take the derivative? Or are you saying you did the product rule and brought the -2 out front? I'm confused as to what you're saying.
I bring the -2 out front of x.
Okay, okay, so you didn't do this. So you treated this like a product rule, right?
Yes,
So you go the -2 out in front of x. Now x to what power?
to -3.
Good, okay, then what?
And I multiply with natural log x.
Good. Plus,
And I did 1/x
good, times
times x over -2.
x to the -2, like that. Okay, perfect. That's your derivative. Good, good. So are you kind of stuck there?
Yes,
Okay, so watch what I write and you just tell me if you follow this.
yes, I see.
Got that? That comes down, and then this one comes down and joins the x that's already down there. Yes?
Yes, I see.
Okay, and now they have the same denominator, so put them together. Like that. And now, if we want to know where the derivative is 0, all we have to do is set the top equal to 0. Right?
Mhm.
And this is going to require a little bit of thinking here. We've got to move the 1 to the other side. We've got to divide both sides by -2, which leaves us with a half. You okay with that?
Yes,
And now to get x, what I'm going to do is I'm going to take e on both sides because e will kill natural log.
yeah, I was thinking about that one. That's why when I get here, I was kind of stuck. Whether I solve through the end and I see an x, that's why I stop here.
Yeah, yeah. But do you get that now?
Yes,
Okay, and this is really just the square root of e, which you could do on your calculator. Now, you also have to figure out where the derivative doesn't exist, right?
yes,
And it looks like from the derivative that you can't plug in 0, right? But you actually have that's a domain problem as well. But so this technically x equals 0 is not a critical number because 0 cannot be plugged into the original function. If you try and plug 0 into this, it's undefined.
I see.
Yeah, so the only critical number you would have is this.
Okay, thank you so much.
Yeah, no problem.
I noticed for what I talked to you about 2 weeks ago about the comment I made to some of the submission, I did not receive the reply.
on the submission for the work?
Yes, I cannot recall like the which one I put the